question on the exam. Once you start looking at it, then it's closed book. But you may take as long as you want for the first question. All right? No books, no calculators, just this way some of the exam is at home to give you more time to do the rest of the problems. That is due at the start of class on Friday. The Sable lunch will be this Wednesday because of March Madness. We're going to be discussing March Madness and entering the pool. How many of you have seen the Fundamental Theorem of Calculus? At this point, this is, who is awake, okay? Your hands should be up at this point. Otherwise, you do not have the prereqs for this course. How many of you have seen a proof of the Fundamental Theorem of Calculus? Of horrors. Okay. Fortunately, within about 45 minutes from now, you will all have seen a proof. I am not going to give the most general proof because you do not want to see the most general proof. I will assume a couple of extra facts about my function so that I can avoid appealing to some results from real analysis. The Fundamental Theorem of Calculus is true in greater generality than what I'm going to show you, but this will allow me to do a simpler proof and really highlight some of the key facts from Calc 1, Calc 2. Any fans of the TV show Friends? What can you tell me about the titles of the episodes of Friends? The one where, almost every episode is that. If this calculus lecture has a title, and it might in the future as we do all this stuff with OIT, this is the one with the mean value theorem. All right? So you have all been warned, when in doubt, what do we use? Mean value theorem. Okay, keep that in mind for today's lecture. It is one of my favorite theorems from Calc 1. So Calc 1 review. So we're going to start with the mean value theorem. Let f be a continuous and differentiable function on the interval a, b. Then there is a c in a, b such that f of b minus f of a over b minus a is f prime of c. I love the mean value theorem. It is one of my favorite theorems from Calc 1. Unfortunately, there is a major drawback to the mean value theorem. It's just there is a c. It does not tell you how to find such a c, but only that such a c exists. Amazingly, for a lot of problems in theoretical mathematics, for a lot of arguments, all we need to know is the existence of such a number, and then it will allow us to do a certain complicated argument. So even though we can't find where c is, it's not so bad. Let's see geometrically what this is saying. If this is a, and this is b, and this is my function, well, we have it like here. Then what I can do is I can draw the line connecting f of a and f of b. And if I look at the slope of this line, that's my average speed. So I'm considering my x-axis time, I'm considering my y-axis distance. The derivative of distance with respect to time is speed. What the mean value theorem says is there is some point in time at which your instantaneous speed equals your average speed. And so in fact, in this case, it looks like there's at least one there, and even one over there. So there would be three choices of c that would work. Here is a quick proof of why the mean value theorem is true. Imagine my average speed is 50 miles per hour. Could I always be traveling less than 50 miles per hour? No, my average speed would be below 50. Could I always be traveling above 50 miles per hour? No, my average speed would not be 50. So either I'm always traveling at 50, in which case it's pretty easy to find a c, every c works, or at some point my speed is below 50, at some point my speed is above 50. And then by the intermediate value theorem, all intermediate values are assumed. I can't get from 50 to 70 or 30 to 70 if I vary continuously without going through 50. So we now use the intermediate value theorem. F continuous on AB, C any value between f of A and f of B, then have a C in AB such that f of little c is big C. So what's going on here is here's A, here's B, and maybe my function looks like this. And so here's f of A, here's f of b. And what I'm telling you is, no matter what value you take between f of a and f of b, there must be some time where under f I go to that. So we're in a world without transporters. I'm moving continuously. If I start 2 miles from home and I end 8 miles from home, then at some point I must have been 5 miles from home. If my speed was 30 miles per hour at one point and 70 miles per hour at another point, it must have been 50 miles per hour at some point. Right? That's the content of the intermediate value theorem. For people who want a more rigorous proof than imagining me driving in a car, I will happily provide such a proof and just post it on the web. But these are the 2 key ingredients we're going to need. Okay, what I want to do now is I want to collect a couple of results that we will use at the end of class. So these are some basic values of sums that are going to be very important. So key sums. So the first is essentially the easiest sum I can give you. All right, I'm going to sum, k goes from 1 to n, the number 1. So I'm going to add 1 to itself n times. So this is 1 plus 1 plus 1 n times. So what do I get if I add 1 to itself n times? N. All right, that one wasn't so bad. The next one is a little bit worse, but it actually can still be done elementarily. I'm going to sum k. So I have 1 plus 2 plus n. So I'm going to sum the first n integers. Does anybody remember what the sum of the first n integers is? Yes?
N times n plus 1 over 2.
Excellent. And now to really push things, let's sum k squared. So this is 1 squared plus 2 squared plus n squared. Anybody remember this one? This one is n plus 1, 2n plus 1 over 6. And these will be useful later in class. The way you prove sums of powers, or at least one good way to prove sums of powers, is through something called mathematical induction. We can actually bypass mathematical induction for the middle one by doing a very clever observation. And so the story is that when Gauss was 5 years old, Gauss saw this in a class that he was in. And so if you were to make a list of top 5 mathematicians of all time, without a doubt, Gauss would be on this dream team. Unquestionably one of the greatest mathematical giants of all time. And in his class when he was 5 years old, the teacher basically told the students to add the numbers from 1 to 100. And now that I've been a teacher for a couple of years, I understand what was going on. The teacher was having a bad day and just wanted to just shut up the little brats for a little bit of time and just have some peace and quiet. And either fortunately or unfortunately for this teacher, Gauss was in the class, and 2 or 3 seconds later, you said 5,050. So how was Gauss able to do this so quickly? Well, Gauss made the very wonderful observation. Oops. 1 plus 2 plus 3 plus n minus 1 plus n. Write the sum backwards. All right, what's s plus s? 2s, that's not so bad. And now, each of these terms, what do they all add up to? They all add up to n plus 1. And so how many of these terms do I have? N of them, so it's n times n plus 1 divided by 2. And so to satisfy his teacher, he just takes n equals 100 and yells out the answer. So this is a really nice observation. We're going to use these results later. Okay. So what I want to do now is I want to state the fundamental theorem of calculus, and then we'll talk about how to prove it. And then at the end of the day, we're going to test the fundamental theorem of calculus. So whenever somebody gives you a new theorem, you should always test and see, is it reasonable? And we'll use these sums to help us do some of these reasonable tests. So fundamental theorem of calculus. And I'm going to assume more than I need, just to simplify the proofs. I don't want to do a 3-week course in real analysis. We don't have the time. We don't even have the time to do all of Math 105. Okay, so clearly we don't have time to add in all the stuff from real analysis. So I'm going to make an additional assumption which will make the calculations a lot easier. So let f be continuous and differentiable on a finite interval AB. Assume f prime is continuous and there is a big B such that f prime of x is less than or equal to b. So this is the assumption I do not need, but it makes the proof a lot easier. I'm assuming my first derivative exists and is bounded. The proof of the fundamental theorem of calculus does not require this. You can circumvent this assumption by knowing a little bit more about real analysis and epsilon delta proofs. Rather than doing that, I'm going to just assume my first derivative exists and is bounded. Almost every function we look at will satisfy this. The only one that really won't is if I give you, for instance, f of x is x to the 1/2 on the interval 0, 1. Then f prime of x would be 1/2 x to the -1/2. As x goes to 0, this blows up. Now this function is still integrable, but I can't use the argument I'm about to give you because the first derivative now blows up. Okay? So a few functions like this fall through, they escape our net, but most functions will work. So I'm assuming f prime is continuous. There's a b such that f prime of x is less than or equal to b. Let big F be any antiderivative of little f. So big F prime of x equals little f of x. Then the area under y equals f of x from x equals a to x equals b, which we denote the integral from a to b of f of x dx. So the important thing to note is this is notation. This means the area under the curve from a to b equals f of b minus f of a. This is the meat of the fundamental theorem of calculus, that the area under the curve is the antiderivative at b minus the antiderivative at a. So here's a, here's b, here's my function. Then this area is f of b minus f of a. So that's the content of the fundamental theorem of calculus. We can find areas by using antiderivatives. Now, unfortunately, antiderivatives are not unique. I can change my antiderivative. If I change f by 5, I don't change its big F by 5. I don't change its derivative. But notice that we have a subtraction here. If I increase big F by 5, then this is 5 larger, and this is 5 larger, and the two 5s cancel. And so the value of that quantity is independent of the choice of big F. That's good because we have more than one choice. I say let f be any antiderivative. Well, fortunately, all the antiderivatives will give the same value. So when we apply this, when we integrate, when we find antiderivatives, we normally get plus some arbitrary constant c. What will we take c to equal? If we want to make our lives easy, what should we take for c? 0, right? Why put it in a constant if we're going to just subtract it off? It's going to just cancel off. Make life simple. Okay, so the question is, how do we prove this? Right? One of the nice things about the proof is we're going to use Riemann sums. And this will be a nice way to see a little bit of sequences and series, which will become a big theme of the course sometime after spring break. So what I want to do, proof, Riemann sums. So L of n will be the lowest sum. U of n will be the upper sum. And what we're going to do is we're going to approximate the area under our curve with lower and upper sums. So what I'm going to do is I'm going to draw a picture over here, and then just leave this picture on the board for the rest of the proof. And this will basically describe what's going on. So over here, here's my interval 0, 1. Here's my function. And what I'm going to do is I'm going to divide my interval up into pieces. I'm going to divide it into equal-sized pieces. Okay? You don't have to do that, but it makes the theory a little bit easier if all the pieces are equal. So this is 0, 1 over n, 2 over n, k over, oh, that's a horrible k. K over n, k plus 1 over n, and 1 is just n over n, 0 is just 0 over n. So this point I'm going to call x0, x1, x2, xk, xk plus 1, xn. So I've divided my interval up into n equally sized intervals. How big is each interval? So how far is it from the left endpoint to the right endpoint of these intervals? 1 over n. So what I'm going to do now is I'm going to blow up one of these intervals just so we can see things a little bit better. So here's xk, which is k over n, and here's xk plus 1, which is k plus 1 over n. So it's 1 over n units further down. And let's say my function looks something like this on the interval. What I'm going to do is I'm going to choose two special points on this interval. These points exist by real analysis. I'm going to choose the point where my function is largest. I'm going to choose the point where my function is smallest. Okay? There have to be such points by real analysis. And I'm going to give them good names. I'm going to call the point where my function is largest uk, because I'm going to be using it for my upper sum. And I will call the point where my function is smallest lk, because I'm going to use it for my lower sum. There could be multiple points where the function is largest or smallest. The function might be constant on the interval, in which case any point would work, and the maximum value would equal the minimum value. But there have to be some points. All right. So let's look at the area under the curve in this interval. I claim that the area under the curve can't be more than what would happen is if I replaced it with a rectangle whose height is f of uk. Gotta be very careful here, okay, right? Because the function is no more than f of uk everywhere else, so the area under the curve can't be more than f of uk times the length of the interval. Similarly, the area has to be at least as large of f of lk. They're off again, right? It has to be at least as large as f of lk, because that's the smallest value of my function on the interval. So the true area under the curve from xk to xk plus 1 lies somewhere between f of uk times 1 over n and f of lk times 1 over n. So f of uk times 1 over n less equal to true area in the kth interval less than equal, whoops, sorry, that's an lk down here, less than equal to f of uk times 1 over n. This is one of the key observations in the proof, is that we've sandwiched the value of the true area in this interval between these two bounds. And now what we do is we sum over n. And so the lowest sum is going to just be the sum, k goes from 0 to n minus 1, of f of lk times 1 over n. And the upper sum is going to be the sum, k goes from 0 to n minus 1, of f uk times 1 over n. So you have to be a little careful with the indices here. Okay? If people are smiling, I'm being very careful with my letters. It's not a bad word. Calculus is fine. All right? Let's think, where do we start? What's the first interval? What's the left endpoint of the first interval? Yes? 0. So we start off with k equals 0, and we go from x0 to x1. Then we go from x1 to x2, and we end by going from xn minus 1 to xn. So we have n intervals. The 0th interval, the first interval, the second interval, we're counting like mathematicians. We're starting at 0. That's why, yes, they're happy we're counting like mathematicians. We go from 0 to n minus 1. How many numbers are there from 0 to n minus 1? There's n numbers, right? And so we do have our n intervals. We just have the annoyance that we start our counting at 0, but we do have our n numbers. And we know the following wonderful fact. The sum, k goes from 0 to n minus 1, of f of lk is less than equal to the true area, is less than equal to the sum k goes from 0 to n minus 1 of f of uk. What mistake did I make? Good, I forgot the 1 over n's. Right? The area in one of these boxes is the height times the length of the interval. The length of the interval is 1 over n. So each one of these quantities is an upper or lower bound for the area under the curve in the corresponding interval. And then if I sum them all together, this will be my lower bound, this will be my upper bound. So what I'm going to do now is I'm going to sketch the proof of the fundamental theorem of calculus. Imagine we had the following wonderful situation. Imagine as n goes to infinity, there's this common limit. And the upper sum and the lower sum converge to this common limit. What must be true about the true area? So the lower sum converges to this common limit, the upper sum converges to this common limit. Yes? Not equal to the sum, equal to their limit, right? Because the upper and the lower sums could be changing as I change n. So imagine the common limit is 18, and imagine the true area was 17. Well, if this is converging to 18, eventually this has to be really close to 18. And this has to be really close to 18. Then there's no way that 17 could work. So the only way it could work is if this was also the common limit. Okay, so this suggests a plan of attack to prove the fundamental theorem of calculus. So step 1, prove un and ln converge to a common limit. And step 2, show the common limit is f of 1 minus f of 0. So you might notice that I'm only working on the interval 0, 1, and the fundamental theorem of calculus talks about an interval ab. The reason is the notation is already painful enough as is. I have xk's floating around, I have uk's, I have lk's, we'll have ck's soon. Why not keep the notation a little bit simple and just start off at the interval at 0 and end the interval at 1? If we can handle this case, we should be able to just go through and adjust the notation to work for the more general case. But this will keep the notation, I can't say clean, but cleaner. Okay? What do you think we're going to use to do step 1? Mean value theorem. Good. What do you think we're going to use to do step 2? I'm sorry? No! Mean value theorem. Right? When in doubt today, guess mean value theorem. If I give you a question such as, what is the statement of the intermediate value theorem? Okay, so yes, mean value theorem would not be the appropriate answer for that. But almost every question today is, what do I do when I'm stuck? Mean value theorem. The difficulty will be figuring out how to apply the mean value theorem. Okay? But when in trouble today, we are going to use the mean value theorem. Now, in some sense, your statement of the intermediate value theorem is not wrong. The mean value theorem is a consequence of the intermediate value theorem. But the mean value theorem requires differentiability, which the intermediate value theorem does not require. All right. In Alcoholics Anonymous or stuff like that, you need 10 steps. Don't ask me how I know. Here we only have 2 steps, much better, much faster. Okay? So let's do proof of step 1. Proof of step 1. Ln, un converge to common value. Which is larger, un or ln? Un, right? Un is always taking the larger points, the points where the function is larger. So we know 0 is less than equal to un minus ln, which is the sum k goes from 0 to n minus 1 of fuk minus f of lk times 1 over n. So we want to show this difference goes to 0. What can we use to control the difference between fuk and flk? I'm sorry? What can we use to control the difference between fuk and flk? Anybody having any doubts on what to do? Mean value theorem, right? What does the mean value theorem say? F of b minus f of a over b minus a is f prime of some intermediate point c. Ooh, f of uk minus f of lk. This looks a lot like something for the mean value theorem, right? By mean value theorem, f of uk minus f of lk over uk minus lk is f prime at some point ck. Ck is in uk lk. Okay? So this means f of uk minus f of lk is f prime of ck times uk minus lk. So f of uk minus f of lk, I'm not going to bother putting on absolute values because I know this is non-negative. This is less than or equal to f prime of ck times uk minus lk. So now I need to figure out how big these things can be. But we made an assumption about the first derivative. We assumed the first derivative was at most b. So this is by assumption. So this is where in the proof I'm using that f prime is differentiable. That f is differentiable. I'm using it to apply the mean value theorem and then to say that not only is it differentiable, I'm now using that it's bounded. So this is some number b. What about uk minus lk? How big can uk minus lk equal? What's the largest that could be? I'm sorry? Yes? Good. The largest it can be is 1 because my interval has length 1. But I can do much better than 1. So 1 is good, but can I refine it a little bit? This hurts. I want something smaller. Little itty bitty. How far apart can uk and lk be? 1 over n. So we know here's xk, which is k over n. And here's xk plus 1, which is k plus 1 over n. So the distance between the endpoints is 1 over n. uk is somewhere in here. lk is somewhere in here. I don't know which one is first. But the distance between them can't be larger than the distance between the endpoints. And so we know the distance between uk and lk is at most 1 over n. Since in xk plus 1. So uk and lk can't be that far apart. What this tells us is the difference between the upper and the lower bounds of the function on the interval is really small. Now b could be a huge number, could be the size of the national debt, could be very large. But unlike the national debt, it's fixed. Okay? It's not changing in the problem. It's some fixed constant. N, however, is growing. We can take smaller and smaller partitions. We're taking the limit as we get more and more, as our partition gets finer and finer. Well, if b is fixed and n goes to infinity, what does that number go to? So what does b over n go to as n gets large? It goes to 0. That's good. Now the problem is, however, how many sums do we have? So how many sums do we have? How many summons are there? N. So even though this is getting small, I have it n times. So something very, very small many, many times could be large, but I get to multiply by the length of the interval again by 1 over n. And that's going to save me. I'm going to get something that's small. And so now we get, therefore, un minus ln is thus equal to the sum, k goes from 0 to n minus 1, of b times 1 over n squared. One of the 1 over n's comes from here, one of the 1 over n's comes from here. This is essentially the easiest sum I could give you. The easiest sum I can give you is when every single term is the same. Every single term here is the same. It's just b times 1 over n squared. How many terms do I have? I have n of them, so this sum is just n times b times 1 over n squared, which is just b over n, and that goes to 0. So we've shown the difference between the upper and the lower sums tends to 0. Okay? Any questions about this? So we use the mean value theorem. Okay, and so now, can people still see if I write 1 lower? Or is that no longer visible? Okay, so therefore, un minus ln goes to 0, so converge to common value. Okay, this is why I was trying to write very high in the beginning. There is a mistake in the last line, and it's worth one free homework problem. I made a small, subtle mistake. So I agree that un and ln, the difference between them goes to 0. And I claim that that implies that they converge to a common value. So the problem is we don't know that the UNs are decreasing and the LNs are increasing. Imagine the UNs were always decreasing. So UN plus 1 can't be larger than UN. So the UNs are going down and the LNs are going up. Well, in this case, if the UNs are going down and the LNs are going up and they're converging to, the difference between them is going to 0, they have to converge to a common value. Okay? Imagine my hand, the height of my hand above the ground represents UN, and the height of this hand above the ground represents ln. Is the difference between them going to 0? Yes. But they don't have to converge to a common, they have to converge to a common, they don't have to converge to a common value. They don't have to converge. Their difference converges to 0, yes, but they could be oscillating up and down, up and down. So the problem is, when you take your partitions like this, you don't necessarily know that the UN and the ln are going to converge. You just know the difference between them goes to 0. There's a way around this, and this is something we already saw when we did divide and conquer, is we can divide our intervals in half. And so rather than doing our partitions first into 2 pieces, then 3 pieces, then 4 pieces, we do it into 2 pieces, then 4 pieces, then 8 pieces, then 16 pieces, then 32 pieces, etc. And when you do it like that, every time you're splitting an interval. And if you split an interval, then the upper sums cannot increase, and the lower sums cannot decrease. And so if you do that, then you're okay. So again, this is not a course in real analysis, but I want you to be aware of the pitfalls. When calculus was first developed, there were a lot of people who attacked it and said it was not built on a rigorous foundation. They were correct. It took a couple hundred years before calculus was done rigorously with solid foundations. And so I want you to be aware of every place where I might be trying to lie to you. So I will not put things like this on your exams unless you ask me for an individual exam, in which case I will happily oblige. But I want you to be aware of the difficulties. Okay? I want you to be aware of where you have to be extremely careful. There are so many statements that seem intuitive, but they may be false, and you have to be careful. All right, so this is step 1, the proof that UN and ln converge to a common value. Any questions on step 1 before we continue the fast proof of Calc 1 and move on to step 2? Okay, so now we have to prove that this common value is actually the antiderivative at 1 minus the antiderivative at 0. What's going to be the key ingredient in the proof? Mean value theorem, good. The harder question is, how are we going to use the mean value theorem? Step 2, proof common limit is f of 1 minus big F of 0. All right. Let P0, P1, P2, Pn minus 1 be any sequence of points such that Pk is in the interval xk, xk plus 1. You get to take any point you want, okay? Then the following is true. The sum, k goes from 0 to n minus 1, of f of lk 1 over n is less than or equal to the sum, k goes from 0 to n minus 1, of f of pk times 1 over n is less equal to the sum, k goes from 0 to n minus 1, of f of uk times 1 over n. So I claim that no matter what sequence I take, the value of the lower sum is less equal to that corresponding sum is less equal to the upper sum. And to see why this is true, here's xk, xk plus 1. Here's my function. Here's uk. Here's lk. So uk gave me this rectangle. Lk gives me this rectangle. Imagine this is pk. F of pk is less than f of uk, so this has to be less than that area. F of pk can't be less than f of lk, so the area under that rectangle has to be greater than the lower rectangle. So it has to be sandwiched in between. So all we have to do is find a good choice of pk among all the infinitely many pieces to choose. Okay, so what are we going to apply now? Mean value theorem, right? We're applying the mean value theorem. That's the easy part of the question. You've been primed, or you should have been primed, to say mean value theorem without thinking. This is the question that requires thought. Okay, I'm going to apply the mean value theorem. I've convinced you. I've convinced myself. What do I apply the mean value theorem to? I need some function to apply the mean value theorem to. What function should I apply it to? That's the tough question. Any thoughts on what we should apply it to? What function did we apply to it before to look at lower sums and upper sums? We applied it to little f. What might be a good thing to try applying it to now? Big F. What are we trying to get to? We're trying to get to f of 1 minus f of 0. So again, in some sense, the entire point of today's lecture is this 1 minute right now. You're going to forget the proof of the fundamental theorem of calculus. Okay? But this one moment, please try to remember. We're trying to get to f of 1 minus f of 0. We somehow have to get big F into the game. It makes sense to apply the mean value theorem to big F. We want big F to somehow come into play. So it's the only function that's still around that we haven't used. So f of xk plus 1 minus f of xk over xk plus 1 minus xk equals big F prime of ck for some ck in xk, xk plus 1 by the mean value theorem. So I want you to see that this is a reasonable thing to try. And now, rearranging, we get big F of xk plus 1 minus big F of xk is little f at ck, because big F prime equals little f. And how far apart is xk plus 1 to xk? What's the length of the interval? 1 over n. So this suggests what we should take for our sequence pk. Let pk equal ck. Ck is from the mean value theorem applied to big F. So that tells us what we should try to do. We're going to take our points to be these ck's. And now what do we get? We get the lower sum is less equal to the sum k goes from 0 to n minus 1. And now we replace the f of pk 1 over n with big F of xk plus 1 minus big F of xk. And this is going to be less than or equal to the upper sum. We don't have the 1 over n to carry over because we needed that in the use of the mean value theorem. The 1 over n is absorbed. Okay? So I said earlier that the easiest sum I could give you is adding a constant, because then there's no change, it's just how many terms do I have. This is actually the second easiest sum I can give you. And I'm going to expand it out to show you that this is actually a very nice friendly sum. When k equals 0, what does this become when k equals 0? It's f of x1 minus f of x0. What do we get when k equals 1? I'm sorry? F of x2 minus f of x1. When k equals 2, f of x3 minus f of x2, dot, dot, dot. When k equals n minus 2, we get f of xn minus 1 minus f of xn minus 2. And then finally, when k equals n minus 1, we get f of xn minus f of xn minus 1. And this is known as a telescoping sum. You know, think of the old telescopes that pirates have that collapse when you push them together. You could be a moron, it's a technical term, and add horizontally and make your life painful. Or you could add diagonally. What happens when you add diagonally like this? They cancel. F of x1 and positive, f of x1 minus, they cancel. F of x2 positive, f of x2 negative, they cancel. F of xn minus 1, f of xn minus 1, they cancel. The only thing that's left is the first and the last term. This is the advantage of telescoping sums. They're very easy to add. We get f of xn minus f of x0. Oh, but wait, the point xn, that's just the point n over n, that's f of 1. x0 is just the point 0 over n, that's f0. Hey, we get f of 1 minus f of 0. So we get that f of 1 minus f of 0 is sandwiched between the lower sum and the upper sum for all choices of n. So we know here's the lower sum, less than or equal to f of 1 minus f of 0 is less than or equal to the upper sum. As n goes to infinity, we know this goes to the true area. And as n goes to infinity, that goes to the true area. So what's the only thing that f of 1 minus f of 0 can go to? It has to be the true area. So these must be equal. And so the true area is just f of 1 minus f of 0. And so this completes the proof of the fundamental theorem of calculus. And so even with all the prereqs and everything, you know, less than a lecture to do. A lot of material coming here. Okay? You know, the key idea was using the mean value theorem, trying to see good ways to incorporate it. Okay. Any questions about the proof? I will not hold you responsible on exams for proofs, you know, that are this complicated. But I want you to see how the argument is done. I want you to have a sense of why we try to do what we do. What were the key ingredients? Why did we need these extra assumptions about f? Also, this was a good way to see sum sequences in series. We saw the upper sum and the lower sum. What I want to do now is I want to test the fundamental theorem of calculus. So whenever you see a new theorem, always test some simple cases and build intuition. So what's the easiest function you can give me to integrate? F of x equals? No, that's not the easiest. Second easiest. 1. Thank you for not giving me 0. F of x equals 1 on the interval 0, 1. So here's 0, here's 1, here's my function. I want to find the area under the curve f of x equals 1 from 0 to 1. What shape is this? Rectangle. So the area is 1 times 1 or 1. All right. Let's check the fundamental theorem of calculus. F of x equals 1. Big F of x equals x. F of 1 minus f of 0 is 1 minus 0 is 1. If this is all the fundamental theorem of calculus could do, it would not be worth learning. Right? This is overkill to find the area of a rectangle. All right. So what was the second simplest function to integrate? F of x equals x. F of x equals 2, I consider the same function as this. So I take f of x equals x on 0, 1. OK. And so now, oh boy, it's a triangle, right? We're going to use calculus to find the area of a triangle. Right? What's the area of a triangle? 1/2 base times height. So the area is 1/2. All right. So here, let's check the fundamental theorem of calculus. So we get f of x is x. Big F of x is x squared over 2. Big F of 1 minus big F of 0. 1/2 minus 0 is 1/2. This is clearly worth the tuition you are paying to go to Williams. Right? This is clearly worth being called the fundamental theorem. Right? We can find areas of triangles too. Right? All right. It should be obvious now, but what shape do we check next? X squared. Life is about to become interesting. F of x equals x squared on the interval 0, 1. Ah. Can anybody elementarily calculate the area under a parabola for me without using calculus? All right, so now finally we have a real legitimate test of the fundamental theorem of calculus. The problem is we now have to find the area of a parabola. Yes?
Wouldn't it be like y minus a quarter of a circle?
Why?
Oh, wait, never mind.
There are these wonderful relations from geometry, and I forget exactly what they're, but they relate the area of this object to the area of this geometric object. So you may be right. Email me your comment and I will check and see if you're right. I don't know offhand if that's correct. Now calculus is easy. We get f of x is x squared. Big F of x is x cubed over 3. Big F of 1 minus big F of 0 is 1/3. So we can find the area easily by calculus, but I want to see, is calculus right? I want to see, do we get the correct answer? So does anybody know a way to check and find the area of the parabola? What could we use? I'm sorry? Ooh, it's painful to say no there. It's on the board. Nope. Yes? Sum of rectangles. And what do I use to calculate the areas of those rectangles? I'm sorry? The Riemann sum, right? We just developed the whole theory of the Riemann sum. To find an area under the curve, you just chop it up into rectangles and add them. So let's use Riemann sums. All right, so let's do the upper sum. So the sum, k goes from 0 to n minus 1 of f of uk times 1 over n. Well, on a parabola, where's the function largest on each interval? At the right endpoint. So we have a sum, k goes from 0 to n minus 1. What's the right endpoint? The right endpoint is k plus 1 over n squared times 1 over n. Okay, so if this is k goes from 0 to n minus 1, this is the same as the sum. I'm going to just reindex. I goes from 1 to n of I squared over n cubed. And when k equals 0, k plus 1 is 1. When k equals n minus 1, k plus 1 is n. So the sum is the same as I goes from 1 to n of I squared over n cubed. All right, so this is 1 over n cubed times the sum, I goes from 1 to n of I squared. Hey, the only difference between that and this is I'm using the letter k here and I'm using the letter I over there. That's not a big deal. So we get un is 1 over n cubed times n plus 1, 2n plus 1 over 6. Ugh. Okay, one of the n's cancel. And we get, if we multiply this out, we get 2n squared plus 3n plus 1 over 6n squared. Or 1/3 plus, now over here, I'm going to have 1 over 2n plus 1 over 6n squared. That's my upper sum. As n goes to infinity, what does this go to? As n goes to infinity, converges to what? 1/3. So we've just shown the upper sum of the parabola converges to 1/3. If we did the lower sum, we would get 1/3 minus a little bit, and that would also converge to 1/3. So this is the first non-trivial check of the fundamental theorem of calculus. These I consider trivial checks. All right, rectangles, yeah, triangles, that's not a big deal, okay? The fact that the fundamental theorem of calculus gives you the right answer there, that's not impressive. The fact that it gets you the area of the parabola, that's now reason to be confident that there's some real content, that there's some real meat to the fundamental theorem of calculus. Okay, so this was basically the entire theory of integration in one lecture plus tests, okay? So we will continue